Max Jackson action. I'm trying to come up
Place, which is not a word. It's a.
I know you need active something else.
Okay, whatever. And that is an M to J. Yeah, no, it's great. Yeah.
Good branch.
Do I have any others? Yeah. No, because that's my go back. Levels. Okay. Now, go look at my grades. User scripts in my browser.
In video. Yes. You're on a deep. That's all. This would be out instead of stuff.
Yeah. No, I'm like, let me show you my commit log.
No more three. That's a preference. Are you ready? Good.
Yeah.
Okay, welcome back. Today we'll start off with a review of the questions on the midterm exam, and then we'll finish up tables. And I'm not quite sure whether we'll actually get to filtering and aggregation, because there's like about 60 slides left about tables. But if we do, we'll then talk about filtering and then about aggregation methods. Okay, what are the correct answers for the midterm and why? So this is kind of like the first question here that you had, like give at least 3 different ways to select. No. Okay, I have the wrong slide deck open. That's 2015. That's better. Okay, so the first question here was on CSS, and so we had two different pieces. We had the code, and then we had the HTML below it, and the goal here was only to simply see whether you guys understood the rules that CSS applies, like these selectors. And so, what is the first selector here, the P larger than B? What does that do? Yes, but what kind of inside? Directly inside, yes. No nesting levels. What does div div space b do? All the b's that are within the div at any nesting level. And then the class is kind of obvious. And so if you go through that code, you can see which parts here are underlined and stroke out or line through. I think that was not a particularly hard question. The second question was about the relationship between source code and the DOM and SVG. So what is the relationship between the HTML shown in the elements window of the inspector and the source code? So what's the difference here between what you see if you go on inspect in the browser and what you see in what you have in the code? So what you see in the inspector is essentially what is dynamically generated as the DOM. So that could be like generated by JavaScript. So for example, if we do implement something in D3 and manipulate the DOM dynamically, we have a representation at that current time point in the DOM, which we see in the inspector. But that's not the same thing as the source code, right? Like if we have a very simple page where HTML is all we use, those two are equivalent. But whenever we use something like JavaScript to manipulate the DOM, then we get a divergence between the source code and the DOM. And the second question is, what was the document object model? So the DOM is this hierarchical representation that is used by the browser to render, but it's also this API to manipulate what is going on there. So this is the DOM API. So it's those both. It's like a programming API, and it's also the hierarchical representation used by the browser to render. And then the C question for this one was, what is SVG? What is the relationship to the DOM? And that's also quite obvious because we've used it so much. SVG is a vector graphics format that can be natively rendered by browsers. This is like true for the last 5 or 6 years. What is nice about the vector graphics format? That we can zoom and it's always like precise, right? We don't have pixels. We don't get any pixelation. And SVG is part of the DOM specification, so it can hence be programmatically manipulated just like HTML. So I can essentially write SVG by hand, and it looks very similar to HTML. Okay, so here we had the questions of what was going on with this code. And so there were two cases, the time point 1 and time point 2. Like here, we started out with this, like a data set with 2 elements, and then we had a data set with 4 elements. And our original SVG contained 3 blocks, as you can see here up to the very top. And so there's 2 problems with this code. The exit isn't handled and the merge isn't handled. And so after time point 1, this is what the screen would look like. The reason for that is that the first 2 rectangles here are like this one, and they are being manipulated, but the third one here, this one here, remains. And so we get the nice styling for those 2 bars, but we don't remove that exit properly for this case. And if we change this to 4 elements in our data set, like as we have here, we have an enter case which we don't handle properly. So here, as you can see, in the enter we just add a white rectangle at position 1010 with height and width 30. So this is like this rectangle that's shown here, but there is no merge. So this enter selection is never properly styled in a data-driven way. This little white rectangle will of course have the data bound to it, but it's not been merged into the selection which we use here to style. And so what did you need to do to actually fix all of those problems? We had to add these 2 lines. Selection.exit.remove, that takes care of the first case, and then the merge here of the enter selection with the selection is what takes care of properly handling the merge for the enter case. Is that clear? Any questions about that? Great. And then we talked about crowdsourcing and graphical perception. This was the class, the question that was only for 6630 students. So what is crowdsourcing?
It's the use of the internet to have a wider...
Well, there's internet in there, that's right. So what we do with crowdsourcing is we set up some kind of like web service where we can farm out some small tasks to a large number of people for micropayments. So like that's very common in labeling images, for example, but you can also use it for visualization evaluation. So we have like some small and short tasks, and then some users, for example, using the Amazon Mechanical Turk platform, can sign up to do those tasks, and they get paid per task. And this is like usually a couple of cents per task, but those are very short. And then you can do many of those and very frequently. And so this is kind of like this paper that we read by Mike Bostock and Jeff Hare was evaluating how we can use crowdsourcing to evaluate graphical perception for visualization cases. So what are the pros and cons of a traditional laboratory studies for evaluating viz? Well, obviously it's cheaper because we can like get many people to do this very quickly. It can be very fast because we have a large pool of users to potentially query, especially compared to laboratory studies, right? If you're a PhD student and you want to do a lab evaluation, you have to find like people, then you'll probably have all your grad student friends who do these tasks, which is probably not a great sample of the population in the first place. You have to schedule them, you have to bring them in, you have to explain everything manually, and then you have to wait until they're done. And so this can take weeks easily for even like 20 or 30 people. But with crowdsourcing, you can get a pretty large number of people to do your tasks. And you also have this potentially increased ecological validity. What do I mean by that? So what is ecological validity?
The ability to extend the results from the experiment to the real population?
Yes, to some degree. Like what ecological validity is a kind of like our like how much we can say about how valuable our experiment is in a real life case, right? Is it a representation of something that is actually happening, or is it something that is very constrained on the laboratory conditions? So the example that was used in this paper was that we had a study that was very dependent, as is not surprising for visualizations, that was very dependent on the quality of the display, the distance of the user to the display, the resolution of the display, the color calibration of the display, and so on. And so if we have a laboratory study, we can, like everybody has exactly the same setup, we have probably calibrated monitor, we can kind of take care of any extraneous factors like light shining on the display and so on. So we can control for all of that. But we can't control for all of that in a Mechanical Turk study. So that is a kind of like we'll get more noisy conditions because of that. But they are probably more ecologically valid because this is a more realistic scenario. So we can kind of like counteract this noisy setup with a larger number of n. So you probably wouldn't run like a Mechanical Turk study with 16 users, but you could easily run a lab study with 16 users. Yeah, and this is like kind of like this increased ecological validity is also at the same time one of the like the reason for the increased ecological validity is also like a part of the disadvantages. So we have lack of the control over the experimental conditions, monitor parameters, viewing distance, and so on. And then subject motivation. Like you can, there's a lot of people in Mechanical Turk that just try to make money without actually doing a strenuous task, and so you have to make sure that you only consider results from people that are actually doing the task in earnest. And that's much easier to control for in a laboratory study. If you're sitting next to a subject, they're not likely to just click somewhere randomly because they are like there's personal things going on between you and them. Okay, the design question. When drawing bar charts or line charts, should scales always start at 0? Why or why not? Anybody want to answer that?
Depends on the data. We want to show the data, not the...
It depends on the data. It also depends on what you want to show, right? So there, like, it's a good rule of thumb, like if you don't know anything about the data, start your scale at 0. But usually, what you want to do is to show an effect that you care for. You have to be fair about representing the data, but some effects can't be shown properly when scaling everything to include 0. And sometimes we don't really have a meaningful 0, like for temperature, for example. And so the rule of thumb that you should follow here is use a baseline that shows the data, not the 0 point. And then we had a question on all general design principles, describe some guidelines for faithfully representing data. And so here's just like a list of these guidelines. If you had 3 of those, that would be fine. Use a baseline that shows the data, not the 0 point. Is kind of what we had in the previous part of the question. Frame the data appropriately. Don't cherry pick what to show. Remember this example with climate change. If I only show you 2 or 3 years, I can't see a trend, but if I frame it correctly to include a wider range of years, then we can actually see what is going on. Show data variation, not design variation. So if we have any variation in our chart, it should be corresponding to data. And then this principle, this effectiveness principle, use the best visual channel for the most important aspect of your data. So the best visual channel being position. So whenever you can use position, use it to show the most important aspect of your data. And then the expressiveness principle was the visualization should show all the data and only the data. So this was this idea of not using anything like chart chunk, and we discussed about the pros and cons of this chart chunk. The next question was on perception, specifically what is pop-out and pre-attentive processing. And so, anybody want to answer that?
Basically something that makes the data, like what we want the audience to focus on immediately upon viewing this.
Exactly. So it's a visual feature that we perceive very rapidly without actually having to look at every item, whether it contains that feature or not. So the classical example is color hue. You will spot this red rectangle here much quicker than you can actually look at every item individually. So this pops out off the screen. And this is extremely rapid. Before focused attention, it is also independent of the number of distractors. So no matter whether I have like 10 of those rectangles or 500 of those rectangles, I will always see the one red rectangle very quickly. The second question was list at least 3 properties that have a pop-out effect, and there's many. There's like 6 shown here: orientation, length, closure, density, hue, color value, brightness. But there's also size, curvature, flicker, direction of motion, and so on. So there's plenty of those. And then the C question here was, what are the best benefits of using pop-out in a visualization? What do you have to be careful about when trying to use pop-out in a visualization? Anybody want to answer that? So why do we care about pop-out for visualization?
Pre-attentive processing.
Yes, but why?
To highlight.
It draws attention to something that you want the viewer to see.
Exactly. So if I want to highlight something, I can use a pre-attentive property or a pop-out property to simply draw people's attention. And we have to take care of actually using it properly, right? Here is an example where we use pop-out properly. We have red dots in a sea of black dots. But if we have too many other colors here, like in this example, we have lost this pre-attentive property. And so like a simple design guideline that I personally use a lot in my visualizations is that I minimize color for the encoding of the data and use color to draw people's attention using a pop-out effect for interactive highlighting. And then the last question was this design critique and redesign question. So we had this 8, like this was the 8 paid by various countries over a couple of years. And so the questions here were the usual ones. So what is this chart? What do we see? What's the data in here?
How much aid the US provides compared to other countries for a few years?
Exactly. And what are the marks?
Areas.
Yes, the areas, the circle segments. What are the channels?
Colors. Shades and color.
Color is correct, but what does color highlight?
Major contributor.
Yeah, only the US actually, like the US versus everyone else. What is the other channel that is used here? Arc length or angle. So what's great about this chart, or what's not so great about this chart?
The inputs are
It's a pie chart, yes.
The inputs are inconsistent. So for example, Germany appears in one of the data, not in the others.
Yes, which is really bizarre. But I think it's always rank ordered here, but it doesn't like make sure that Germany is, like we can't really read where Germany is in these other cases, right? Can we see, like, do you know what this segment here is? No, okay. And can you see how this segment here changed over the time? So what does this chart actually show us?
Just the US portion.
Exactly, just the proportion of the US. And yeah, it doesn't even show us the total sum, right? It could be that the US kept increasing the total number of dollars they spent on aid, but just everybody else is catching up. We can only read that from the table. And so what were some of the redesigns that you guys came up with?
Bar charts.
Group bar charts would be an option. The other simple option would be
Line charts.
line charts, exactly. So it's pretty simple. And I would also probably redesign the table to kind of like have at least some consistency, like each row stays for a country, and that I could encode the ranking of the country maybe in some different way. Or I could show like some slope charts between those to see where they change in rank. So kind of like reintroducing some relation of where a country is. And then one other thing that I noticed in this chart that I don't know whether anybody you noticed, what is tricky about like this here? I actually don't know what they do here. They have Germany, UK, and EU. It's kind of like, what does it mean? Is it the rest of the EU? Or is it the EU plus Germany and the UK? It doesn't seem to be like that because the EU is smaller than Germany, right? So it's probably other in the EU, but it's very ambiguous, right? We can't actually know from this chart. Okay, so this was kind of what we had on the midterm. Any questions about the midterm? So we're in the process of grading it, but it'll be taking a while until you get the grades because it's a lot to reach for us. Okay. So yeah, last time we talked about tabular data visualization. So we started out with a couple of simple things like bar charts and line charts and so on, but then we kind of graduated to more complex visualizations, like more complex explicit tabular data visualizations. And then we talked about heat maps or pixel-based displays where each cell is a pixel, and we kind of like saw the problems and the principles behind them. The key thing is that we need to properly order this, and again, one of the important things in this slide deck is this slide here, is like the analytical component that we need for tabular data visualization. So if we don't want to do anything algorithmically or do any like machine learning or on a data set, if you can call clustering machine learning, then we can use something like scatter plot matrices or parallel coordinates. If we like use a heat map, we need to do some smart reordering. If we don't have any predefined orders, and we typically use something like a clustering algorithm for this, or some other matrix ordering algorithms. And then if we have visualization techniques such as multidimensional scaling, we have a very strong analytical component. We're mainly showing derived data. And so I'll be talking, if I have the time, about clustering and projection methods in the second part of this lecture, but now we'll be talking about axis-based techniques, parallel coordinates, and scatter plots. Okay, so spatial axis orientation. We have these like 3 different types. We have rectilinear, parallel, and radial, and any variations thereof. that we can use for axis orientation. So here are these two core examples. We have a table with 4 different dimensions: math, physics, dance, and drama. And we show, like this could be scores in the subjects for individual students. We can visualize these either as a scatterplot matrix. In a scatterplot matrix, we have every variable plotted against every other one, or we can visualize this as a parallel coordinates plot where we have math as an axis, physics as an axis, dance as an axis, and drama as an axis. And there seems to be like a correlation in this data set between math and physics, and it is kind of like seems to be anti-correlated with dance or drama. And let's look at whether this is true here too. Yeah, so we see the same trend in the scatter plot as well. Okay, let's talk about the scatterplot matrix first. The scatterplot matrix, which people also say SPLOM, is a matrix of size D by D, where D is the number of dimensions. Each row and each column is 1 dimension, and each cell plots a scatter plot of 2 dimensions, where you then can easily compare those 2 dimensions. And so this here is this classical example of the flowers data set that is used in machine learning a lot, with sepal length, sepal width, petal length, and petal width. What is the relationship of the elements to the right of the diagonal to the elements to the left of the diagonal? Anybody see any patterns here? Yeah, we see the same thing, it's just flipped over, right? So in theory, everything would be contained in just using the lower diagonal here. So we actually wouldn't need the upper, or like we would only need one of them. It still usually doesn't make sense to not draw the other one, because it simply is like easier to read. We can go in both directions, and we kind of like, since most view visualizations are rectangular, by saving like a triangle doesn't really make too much sense here. Let me see whether this is an interactive example. Yeah. And so what is usually very useful in scatter plots is to combine it with brushing, because then we can see like a global pattern. This is also like a nice pop-out effect that we have here. Like here I've selected a cluster in one, this is sepal length versus petal width. So we see that both tend to be short in many of those flowers, and that is consistent with sepal length plotted against petal length. So, and then we would assume that petal length and petal width is also correlated. So we see here a linear correlation. We see, but here we also see like a non-linear correlation, like between petal length and sepal width. There are some that are correlated, but some that are actually not linearly correlated. So we see these nice cluster outliers in this scatterplot matrix. So if we analyze a scatterplot matrix, we have limited scalability. Like these matrices tend to be pretty big. So more than 20, like a matrix of 20 by 20 is already pretty small. And you can do about 500 to 1,000 records. If you do like a naive, or let's say not quite so naive implementation for 1,000 records. Brushing, as you just saw, is very important. And this is often combined with a focus scatter plot as a focus and context technique, especially if I have larger sets of scatter plots. I'll show you an example in a second for that. So, and if you want to enhance a scatter plot, you can use algorithmic approaches. For example, you can cluster or aggregate records. You can also choose the dimensions. Sometimes, like if you have a very high dimensional data set, you might not care about some dimensions, right? You could run an algorithm to show you only the 10 dimensions that capture most of the variability of a data set, versus leave those out that are not that interesting. And then you can also optimize the order that you see the effects, like in which order you plot these plots. So what do I mean by limited scalability? In terms of the items, we can do this like smarter approach of, instead of plotting individual pixels, we can kind of like create a grid and bin into that grid to represent larger data sets, and then we have more like a density plot instead of an explicit scatter plot. This here is a nice implementation. Here I'm actually visualizing 100,000 data points in a browser. I can actually switch to 1,000,000 data points. Let's see how long it takes. So now I'm visualizing 1,000,000 data points in the browser, and I can interact with it. What is the problem of like any of those aggregation methods? Can anybody think of anything? What happens to like a potentially interesting outlier? We might like lose an outlier, right? If I have in this data set, if there's one item that is down here, but I'm calculating this and using a color map for 1,000,000 data items, then I probably won't even recognize that there is an outlier here. And there are some outlier preserving algorithms out there that try to do that. Here's an example of a focus and context scatter plot matrix. So what we have here is the scatter plot matrix in small. This is the cars data set, and then for one selected one, the red one here, we show this in detail. This is horsepower versus displacement, and you can see that bigger engines that have more displacement typically also have more horsepower. So we have this like a linear trend in here, and this, like I think I showed this video when I talked about interaction.
This application is a prototype implement a scatter plot matrix, a query layer control box, and
but I'm just going to show this
a set
again.
of simple navigation techniques allows for controlling the position in the scatter plot matrix.
So you see
The
that
keyboard or the navigation bar can be used for stepping one position in the matrix.
you see that this is like a essentially we have the matrix here, and then whenever we like navigate to another combination of dimensions, the chart in the background is dynamically updated. And this paper also has some kind of nice transitions between those dimensions. Okay, the next topic. One point that I don't have on the slides here, but what is another way of dealing with a lot of points in a scatter plot? So let's say I have a scatter plot like this, and I have like 1,000 points, not 1,000,000 points, but 1,000 points. What could I do to see dense clusters? Because otherwise, like if I have dense areas, I couldn't like reasonably distinguish them from other areas that are not quite so dense. One easy trick is to use transparency for your dots, right? To use like a 0.3 alpha value, and then you can, like if there's many points on top of each other, you can still perceive this as a darker area, which is actually done in this example here. So you can see that we have some transparency here, and that here, like whereas there's a lot of dots on top of each other, we can see that they overlap, yeah, there's not too many dots. Here's a good example where I see this a little bit more. But you could do this more aggressively. Of course, if you have too dense areas, you have to go down with your transparency, and then you start to lose outliers again. Okay, next we'll talk about parallel coordinates. And so in parallel coordinates, axes represent the attributes, and the lines connecting the axes represent the items. So here is the example for a scatter plot with the dimensions x and y and points a and b. And that would be where those are in x. In x we have a is high and b is low. In y we have a, b is low, and b is high. And then we connect them with lines. And so we see that those have exactly an anti-correlation between them. Here we see like an example that for, again, the scarce data set. I showed this before, but now let's talk about it a little bit more formally. So what can we see here in the relationship between miles per gallon and number of cylinders? What's the relationship we see here? Inverse relationship, exactly. What is the relationship between miles per gallon and weight? You can't really tell, right? What's the relationship between weight and acceleration? Inverse. So what we learn from this is that Parallel coordinates work well for judging neighboring dimensions, but they don't work so well for judging dimensions that are further apart. And if I want to judge dimensions that are further apart, I have to use some kind of interaction. And so here, like, I'm now selecting the 3 or 4 cylinder cars, and I can see that they have like high miles per gallon. They have low displacement, low horsepower, low weight, low acceleration, or high acceleration. But that's probably not completely consistent, and they're made across multiple years. And so how is a parallel coordinates plot different from a line chart?
It's just that every axis is a different scale and different attribute that you're doing.
Exactly. And that's a nice property, right? We can visualize tables that are otherwise heterogeneous. So if we think about this example that we had with the heart rate and like the different, the time for 100 meters and the time for like the distance that somebody could jump, we could plot that easily, and we could see that there's probably a correlation that fast people also can jump far in a parallel coordinates plot. One limitation is it's not super scalable. So here is a scatter plot, like a parallel coordinates plot with 1,500 dimensions. And I even didn't draw the axis here, because if I drew the axis here, it would just be black. We wouldn't see anything else. And this is actually the first visualization that I ever made in my life. And I was very disappointed. It's a parallel coordinates plot with random data. And you can see this is not a lot of data, but I just didn't use any transparency here for these lines. And then I used transparency for these lines, and then we can see this trend that is basically random data. By the way, this is a good tip. If you ever create a visualization, always look at your visualization using random data to see whether you actually can identify it as random data, because you actually have to learn a little bit. It looks like there's an anti-correlation here, right? But that's because these like lines that go from the top to the bottom, they are the longest and they tend to dominate the plot, but it's actually random. So how can you address the scalability of many items? Transparency is one thing. We can bundle and cluster. I'll talk more about this, but we can also sample. And this is often, like if you have a large data set, sampling is a very effective strategy. You can essentially often create a random sample of your data set, and you can still see most of the trends. So there's pretty sophisticated, it's pretty obvious that many trends remain if you just randomly sample, but there's also better methods that have some error bounds for sampling. So how can we fix this problem with the adjacent axis? Well, one of them that I showed earlier is brushing. The other one is interaction by reordering the axis. So here, like if we want to see the relationship between miles per gallon and acceleration, we can simply drag one of the axes to be adjacent to the other axis. So we can let the users change the order. We can also automatically calculate an optimal order to always like juxtapose like very different dimensions. And then we have another problem in parallel coordinates plots that's a little bit more like detailed. We have a line ambiguity, right? If we have lines coming in here and intersecting at exactly the same point, we don't know whether this is line A or B, or this is line A or B. It's simply unclear. And there's two solutions to this. The one solution is interaction, of course, because then we can clearly see if we color highlight one of the lines. And another solution would be to use curved lines. So here it's pretty obvious that this is we assume that we have good continuation. So we assume like it's pretty obvious that curve A, like this is A, and not that there is like a discontinuity here, that this here transitions into B. That is a little bit tricky, of course. Like it gets complicated, and I don't know whether this is a super sensible solution if you just care about general trends in your data set. So kind of a summary, parallel coordinates show primary relationships only between adjacent axes. They have limited scalability. We can visualize like maybe up to 50 dimensions. and up to 1 to 5,000 records. We have to use transparency of the lines for all but very small data sets, and interaction is really crucial here. We have to do access reordering, brushing, and filtering. And we can use algorithmic support to choose dimensions, to choose the ordering of the dimensions, and to cluster and aggregate records. And what do I mean by cluster and aggregating records? Well, there is, like, if you have large data sets, you can simply run, for example, a clustering algorithm, and instead of representing every data item, you can just represent, for example, a cluster centroid and how the cluster centroid behaves. And so here, this is a data set where, like, this is the original data set, and that was clustered, and I think that's the case, yes. This was clustered, and it shows only a representative element for every cluster. And so here's another example that does essentially the same thing. Here it represents a cluster centroid plus the variation of the cluster, instead of showing every single data item. There is kind of like another example for this. This is like hierarchical parallel coordinates. Here they've used hierarchical clustering algorithms. We'll talk later more about those. But the property of hierarchical clustering algorithm is that I dynamically can define how many clusters I have after I have clustered, right? I can cut this dendrogram at multiple levels. And if I simply represent the whole data set, this would look like this. And if I start cutting it so that a couple of additional clusters emerge, I can see like this big, this very different cluster here on the top. And then if I increase the number of clusters, I get more and more to the original representation. A closely related technique to cluster to parallel coordinates is the star plot. So here we have essentially the axis radiating from like one common origin instead of being in parallel. Can anybody think of advantages or disadvantages for this?
You can represent data of 1 and 3 in multiple dimensions. I mean, like multiple categories. Like, so for example, in our design critique question, we could have used a color to represent a country and use the lines for different years.
Yes.
And show their contributions.
But how does it apply to how does it apply to an advantage or disadvantage of a star plot?
You can see the trend. You can easily compare every element to the others.
Yeah. Okay. But what I kind of was getting at it was what is compared to a parallel coordinates plot. What would be a disadvantage of a star plot or an advantage? Like they are very similar, right? But what is an obvious disadvantage or an obvious advantage? So one disadvantage that we have here is that the lines overlap more as I get closer to the center, right? Like if I have, let's say, a change of twofold from here to here, from like accuracy to collision to those two dimensions, it's going to look quite different than if I have the same change out here. Like these lines are going to be much more dominant. So because we don't have, like depending on how the distance is here, like the lines are going to be less prominent if the values are lower. And so everything in the center tends to be a little bit more cluttered. So I would say this here, like the star plot, tends to emphasize high values and outliers. And so like this is a star plot that uses multiple dimensions and the same plot. What is also quite common is to use a star plot for every single, let's say, row in the table separately, and then have little glyphs. So I like this visualization here. So this is a data set of all the single malt scotches in Scotland. And you have like the taste profiles of these scotches. So you have fruity, floral, body, sweetness, smoky, honey, spicy, nutty. And then you can scroll through and kind of like see the different taste profiles. And if you look for something super smoky, like here, Lagavulin is a super smoky whiskey, right? And so we can see that it is like a very extreme extreme whiskey in the smokiness direction. Lafroig is the same thing. It is a little bit sweeter, but smoky. So like here we have like maybe 150 or so whiskeys, but notice that I actually have to scroll. Like this is like an interesting visualization, but it's not very scalable. But we also couldn't just plot all of those on top of each other. It would just be really hard to read. I talked a little bit about this. Here is an example for sampling. So like one approach to reduce data is to not show every element, but show some random subset. This is like from a paper. This is the same data set. In the one case, it's not sampled and you can see only black, and in the other case it's sampled and we can see the trends in here. One thing that is important if you ever implement something like this with sampling and have like a data backend, if you ever like run any queries on the backend, you can only apply the sampling for display purposes, but any query or filter that you run should still apply to every data set. And then for filtering, you can like either use filtering directly on the dimensions, or you can filter based on any other criteria, things like minimum variability, specific values for one dimensions, consistency in replicates, and so on. And all of this can be interactive and combined with sampling. And then there's a large class of hybrid visualizations. This here is a cool paper by Jark van Wijk's group. And the idea here is to simply let users place axes dynamically on a canvas, and then either connect those axes with lines and create something like a parallel coordinates plot, or scatter points between them and create something like a scatter plot. And so you can see that just with this simple principle, he replicated like a couple of published charts, like this here is a scatter plot matrix, a parallel coordinates plot, a radar chart, or that we just talked about, or something like a hyperbox or the time wheel, which are like visualization techniques that all have been published in the past, or even crazy things like this. And there's a nice implementation of this. Which seems to have been removed. Oh well, I should have checked that link. Anyways, this is an implementation of this where you can actually do this yourself and draw on the canvas. I'll see where I can find where this would move to. And this also shows a couple of things. Here's like a parallel coordinate plot, and then there's a scatter plot overlaid, and then there's like a kernel density estimate overlaid here on top of these axes too. This is another example which is called connected charts. Here every data point is connected to the lines in these other views. So we see, like for example, that this peak here in program usage is shown here, and then in terms of network usage, it goes to one of those lower values. Combined with brushing, I can quickly identify each of those items and so on. So we can kind of like create those hybrid charts. And I've shown you this before. Like here, we're combining different kinds of visualizations, like the spatial axis orientation with pixel-based heat maps, and with categorical visualizations, and with some like summary statistics. And so we can create these combined visualizations. A special case for spatial axis orientations are parallel sets. Parallel sets are especially suitable for categorical data, or actually only suitable for categorical data. They're very similar to parallel coordinates, but they work with discrete categories and smaller numbers of values, and they also don't have an applied ordering between attributes. Okay, what do I mean by this? This is essentially, this is actually the better example to illustrate the problem. Remember the Titanic data set that I showed before? Here we have like one dimension that simply gives us how many people have survived and how many people perished on the Titanic. Then here we have how many people are female, and you can see there is 20% female, whereas like 79% male. Here we have age, only divided by child and adult. We can see that there's very few children on the Titanic. And then we see class, Second class is actually smaller than first class. Third class is the biggest passenger, and then crew is actually also quite big. And so we have these categorical dimensions, but this visualization technique actually shows us the relationships between them. So if we select survived here, we can see what are the survival rates for females versus males. We can see that the chunk of women that survived is actually quite high, whereas the chunk of males that has survived is numerically is approximately the same as for women, but as a percentage of the passenger, we can see that the majority of males actually died on the Titanic. And then we continue splitting up from here. This is now all of the, this here is all of the males that survived. Now we, down here in this particular band, we have all of the males that are adults and that have survived. And then down in this band here, we have all of the crew members that are male, that are adults, and that have survived. So this gets increasingly, let's say, fine-grained as we continue with those dimensions. What is potentially problematic if I add a couple of other layers here? It gets to be very, very lots of thin lines, right? Instead of having these major chunks. And so this visualization technique, it's a little bit tricky with interaction, but it supports some reordering. And I don't know whether it supports reordering in this direction. I don't think so. And so this is the original technique as it was published. Very simple, very similar. Here we have we start with at the top level with the classes, and they choose one of these dimensions to color them by. And then here it's colored by the first element here. This is housing income, low, middle only, high, mid, and high. And then we have different family types like unemployed, working family, or working single, working with children, and so on. And what is interesting here is that they show also a histogram of distribution of people in for each of those dimensions. So it's kind of a combined, layered visualization, multiple coordinated view. We can reorder them to essentially reduce the crossings. So here, for example, crew and third class is exchanged between those two pictures. And you can also aggregate them. If you want to say, I just don't want to treat second and third class separately, you could instead merge those two, and then you have cleaned up your data set a little bit and have a second and third class, which also reduces the clutter down and further down in the visualization. And then you can also filter, remove one of those, and then in this case you only see the first and the second class on the Titanic anymore. Similarly, highlight, and so on. Okay, so the last tabular data visualization technique that I wanted to talk about is space filling visualization techniques. And that's more of a historical side note. They're not really used too much anymore. And of course, the heat maps and matrices fall into this category, but I'm talking about a special case, which I call these dense pixel displays. For example, the VisDB system. Here, each data item is represented by the color of a single pixel, and we can fit as many items on the screen as there are pixels. So that means we can fit millions of items on the screen. But however, this relies heavily on color coding, and then of course we have the challenge of what is the layout. And so the simple heat map is simply a grid layout, but there's also these approaches where you have a non-grid layout. This looks a little stupid. Where you have a non-grid layout. So use some kind of curve or Hilbert curve or some spiral and so on. And order them by relevance. So for example, have the most important items in the center, but you could also do this for multiple dimensions. So here would be an example where we have a relevance factor and then 5 dimensions in this little glyphs, and then order them in a spiral. So what is potentially the problem with this technique? Here's a an example. Can anybody read something?
No.
No. So I think that these are like interesting from a historical perspective. This is a '94 paper, right? But like visualization essentially has moved on beyond them. It doesn't really follow good visualization design principles. And basically I'm showing this because when I started out like in grad school and I started like my advisor didn't know too much about visualization. He was an augmented reality guy, and I essentially just read papers. And not everything that you see in a paper is good. You have to use your own judgment, and especially in visualization, if it's before 2005, I would be hesitant to trust it right away, right? Take everything with a grain of salt. Simply think about what we talked about. Does it follow those good visualization design principles? The field is not very old, right? Like the InfoVis conference, which is essentially what we're talking about here, was held for the first time in '96. And compare that to math, which is like has thousands of years of history, right? Which is of course nice because we still can come up with new things, and not everything has been researched yet. But then there's also these problems. Like there's so many papers out there that discuss some variation of parallel coordinates, some like nice bundling or some other approach to parallel coordinates. But it's like probably not super useful in the long run. Okay. So that completes the tabular data visualization slides, and now let's talk a little bit about filtering and aggregation. Oh, and before I do that, because it segues so nicely, I wanted to recap quickly views, because like this is a little bit, no, not views. The interaction slides. Because essentially it's like we talked about filtering when we talked about filtering and querying, when we talked about interactions. I quickly wanted to recap the most important points of interaction because it's so important. Okay, so we talked about in interaction about the spectrum of static content versus dynamic content, and like interaction is of course only interesting in the dynamic content. And here we had like autoplay with animations, but the actual interactive content where the changes are the result of user actions. And so why do we want to use interactions? It's because the data is too big, too complex, and there's too much data to show, and there are too many ways to show it. And so why do we, like interaction also amplifies cognition. For example, by like brushing something, I can see it across, like I can quickly identify the same variable across many dimensions. We can observe cause and effect. And so here's like this example that I showed today of direct manipulation, where I directly select in the data space with a rectangle the items that I care about. This is compared to using a query or a slider or something else. So like I could also have like a slider here for dimension x and dimension y and specify this is the range that I want, this is the range that I want for y. But usually direct manipulation, whenever you can do it, is the better approach. We had these types of interaction for single views and multiple views. Single views we show change over time, we do navigation, we do semantic zooming, filtering and querying, focusing context. And for multiple views, we do selections or details on demand, linking and brushing, and adapting representations. And so like after I'm done with this recap, we have talked about this stuff in the multiple view lecture, and we'll be talking more about filtering and querying in the second part of the lecture today. So for navigation, we have pan, zoom, and rotate. That's really mostly important when you have spatial data, because otherwise you usually try to represent things on a screen, except for like simple things like scrolling. Then we talked about semantic zooming, and semantic zooming is essentially this idea that when I like drill down into a part of my data set, that I dynamically show more information about those items that are zoomed in. So here this is this example of this performance, like system performance visualization. We have like just the color coding for the smaller pieces, and then once we zoomed in into one of those aspects in this network file system, in this case, we can actually see a full-grown line chart with labels compared to only spark lines here at the top. And so representation adapts dynamically on a zoom level for this visualization technique. We talked about focus and context. Here we carefully picked what we show and hint at what we're not showing. This is like a synthesis of visual encoding and interaction. So users select a region of interest through navigation or selection, and then we provide context through aggregation, reduction, or layering. And so this is an example of a focus and context technique for like the theme river technique. This is essentially like a stream of things. Like here, we can see that this is like some kind of whatever, like emotional states of a population or being things that are, for example, reported on Facebook. And we can see that we have this very large curve, and then the people have selected this is kind of like our area in which we show a little bit more detail, and then here in this red area we show even more detail. And so we have a focus area, show some like second level or first level context in here, and then show some second level context down here. So basically these tails of the distribution. And then we talked about this degree of interest function, which is based on two terms. Like assuming you have, like you're looking at something currently, you have selected something, you have each item can be assigned an a priori interest, like how important is it independent of my current selection, and then a distance to my current selection. And the degree of interest depends on the a priori index and the distance to the current selection. And we've shown that, for example, with these trees, this degree of interest trees. We talked about distortion, where we used geometric distortion for the contextual regions to make room for details in the focus regions. And as you remember, I was kind of critical about that. Here is the perspective wall, which is kind of like shows you how files have changed on a hard drive over time. And kind of the idea here is that this, like the center area, it's readable, but you can still get a sense of what is going on back there. You can't read it, but you see that there's a lot of stuff going on. And then we had these hyperbolic geometries, or these fisheye views, and so on. And then we had a couple of other examples, and we talked about that these examples tend to be difficult to like reconciliate what is outside of the focus region and what is inside the focus region. We have these problems with navigation, with picking, and so on. And so, like the segue to the rest of this lecture is the filtering and dynamic querying. I just want to recap the Schneiderman's mantra. It's overview first, zoom and filter, and details on demand as the visual information seeking mantra. So what does that mean? Like when we look at the data set, we first want to see what is in the data set, and then let people zoom in aspects that they find interesting, or filter out things that they don't find interesting, and then reveal details on demand about those. And then we had this example for the dynamic queries, where I'm sure you remember this home finder, where you can set multiple points. This is like the Washington DC area. You can see Washington DC itself here, and you can set multiple points, like in this case here and here, and then you can define homes that you care about, which are shown like as white dots here. You can define them by the distance to A and the distance to B, the number of bedrooms, and so on. So this is like it's an early example that introduced dynamic queries, which is kind of related to faceted search. And I have actually an exercise for this. I think that let's just do this exercise now. And so the exercise, like what is interesting about this tool is this really applies all of these queries and filters to only one criteria. But what happens if I wanted to say have two different search criteria? Let's say I either want to be close to the center, or it should, like if it's further apart, it should be cheaper. And I kind of want you to think about how can you redesign this query interface so that users can apply different filters to different areas. And then you should also think about direct manipulation, right? This is an example of indirect manipulation. I have these sliders here, and everything that changes is shown in this chart. And I would like you to think about which of these variables is suitable for direct manipulation, and how could you integrate the direct manipulation in a chart like this. And then I don't also have an idea about like what is going on with these sliders, like what happens if I change any of those sliders. And I would like you to think about how can you show, how do I say it? How can you show the distributions of the data below those sliders in some ways. And so you can do this in teams. We'll take 15 minutes and think about those interfaces. Yeah, if you can help.
I didn't do anything.
I also have scratch paper if anybody needs some.
Yeah, so then like if you want to customize another area, yeah, what's the set? Inside the box, the
language that they talk okay. So I kind of take notes and then later try to discuss with them again, here. So I have just taken a few lines from plus this stuff here.
like a two variable function.
Yeah, you also have like sort of discussed and written in this stages of better, I think. Like there's a guy called Mario. But Mario
room number and date. Room number and time.
It's in the announcement guide, so I can't really change it. But you can from 12 to 1.
Let's go to that.
Like this. To how long program for
Well, like, Or even like instead of blowing up, just like active point, right? Say like take this region, quick point, a line drag, so you might want another point bounce, that you can that's like easy to use. Like it's exactly based on the and you can also like drop down to it's like Squarespace.
Does anybody want to share this with the class? Explain it? Anybody think they have a good solution? Is it hard? Anybody have an approach? What was your approach? For the direct manipulation, what did you identify as? What of these attributes could you use for direct manipulation? On the map, anybody identified an attribute to be used for direct manipulation?
Distance.
Distance. Yes. So I have also played while you guys were writing, so I made a sketch. Let me see whether this syncs. Well, so anyways, you could just draw a circle for the distance and then simply directly manipulate the circle. How did you approach the problem with having two different selections? Anybody want to say?
Like one thing we thought is to do like a brush or something for an area, and that will kind of pop up like a separate like menu for criteria.
Okay. Anybody else have another approach? For like showing two different things? Nobody? What did you use for like showing the distribution of the homes available for each of these dimensions? Okay, so this was my solution. Like I did exactly what you guys described here. I played around with direct manipulation, like showing a circle, showing the distance to A, and then like this is supposed to be a mouse cursor, and then you can drag this around and essentially do a direct manipulation, and that would be synced to the selection here. And then I did like the thing distance to A, and then did a distance to B, and I allowed people to define two different distances here. So I said I have a B1 and a B2 distance, and I did show both of them. And then further down, I introduced like what you see here in the background is like I solved the third problem of how we show the distribution of homes by drawing a histogram in the background of the sliders, right? So I kind of integrated the sliders with a little visualization of the distribution. And so I can kind of like get a good sense of how many homes I'm adding before I actually do an action. And then down here, I allowed people to add multiple circles. And then it gets a little bit tricky, and I'm not saying this is the best possible interface, but then I can do logic combinations of these prior filters, right? So like here I'm subsetting all of the houses that are in A and in B1, or like a separate column for all of those that are in B2. So that could be something like either I want to live really close in a big house to B2, or if I can move closer to A1 or in B2, it has to be a little bit cheaper. And then I could keep doing additional variables here in parallel and show two of those widgets. I'm not saying this is like the best solution necessarily. I also had only 10 minutes here. You could conceivably try to come up with those brushes integrated instead of duplicating them. That could get a little tricky, but is more space saving. So does anybody want to share theirs? No? Nobody wants to share theirs. Okay. So let's call it a day then. I'll see you guys on Tuesday.